All right. Welcome to today's lecture. We'll go straight ahead and then continue from last week. So I'll just do a quick recap of last week's lecture, and then we'll look at what we have for today. All right. So last week, Friday, when we met, we spent pretty much the entire time looking at a three-moment equation method. And I explained that this method is one of the methods which is used to determine the support reactions and then draw the shear force and bending moment diagrams for statically indeterminate structures. So that requires to where the three equilibrium equations might not be adequate to solve. All right. So we perform some analysis using the geometric approach whereby we assume continuity at a support. That's okay. The rotation of the slope on the left side of a support will then be the rotation on the right side of the support. So based on this continuity of the slope at the elastic curve, we're able to formulate an equation which we call the three-moment equation. All right, so we have this equation right here in this space. Okay. All right. So for any set of three supports, the middle support will be the support under consideration. Typically, we are looking at interior supports, will be the support under consideration. Then we look at the moment or the supports on the left and then the supports on the right of that particular center support, and then formulate equations for it, and then find the redundant moments, which are typically the ML, which is the moment on the left, the MC, the moment at the center, and then the MR, the moment on the right. So here my ML, in a way my ML, okay, I wrote it over here. So here my ML is the moment A, my MC is the moment B, and then my other MC, funny enough, is the MR. So the first C is the center, and then the other C is just the letter C. Okay. So we went through a typical example on how to use the three-moment equation method. All right. One of the key things is that when we are trying to analyze it, we assume that because of the redundancy and then introducing these redundant moments, we can also assume that for each span, they are simply supported, so that we use that analysis or that analogy to arrive at some calculations. All right. So in solving these types of questions, we first draw the bending moment diagram, assuming that the different spans are simply supported, which makes it easier for us to draw. Okay. So this example, we had that case, we drew the bending moment diagram for the two separate spans, and then we calculated the A1, the A1, the A2, the X1, the X2, just trying to complete the equation with the known variables. Okay. Then from there, we were able to formulate the equation. Formulate this equation right here, or have the replace the variables with the actual computed values, and then we're able to find our moments, MA, MC, because they were at the end, so they were both zero. Then from there, we're able to calculate the moment at the center, which was -24 kilonewton meter. Okay. Then from there, the next step was to calculate the support reactions, and then also in calculating the support reactions, we can treat each span different. All right. So here we have on this side the first span, and then on this other side the second span. So each one will be assumed to be a different structure on its own. And then, so that's one way to do it. Assume that it's a different structure on its own and then solve for it. The other option to be, if you take the the support B, once you treat it at different different, if you treated different spans as though they were different um simply supported beams, then at B, each end will have its own internal moment, which will be the minus 2.4. All right. But if you want to bring together ABC as a complete structure, as it was in the example, then these moments, which is at B, will cancel out. All right. So it becomes minus 2, 4 on the left is going counterclockwise, and minus 2, 4 on the right is going clockwise. So once we sum the two up, it will give us 0, right? So if you join the two spans together to get a complete structure, then you will not find the moment of the B in here, right? You won't find any moment over here, even though internally, if you break it apart, that moment is there. Once you join it, they cancel out, right? Because they are internal moments. Then, so you can either use this approach, the first approach where you break it apart, or you can use the second approach. So I have the two of them on both sides. The first, the one on the left, which is this section right here, um, deals with a complete structure. All right. Then we can draw the bending moment diagram and then the shear force diagram. All right. The same way also, we can do that for what's the name? Either separate them and then join them later. We end up with the same answer. Okay. So I also explained that there are different ways by which we can draw the bending moment diagram. All right. I would prefer the first approaches, but then there's a way where you can superimpose the two moments and then draw um, bending moment diagram. So usually when you superimpose, the values of your highest points are slightly different than if you draw them stepwise. Okay. Either way, it's fine. We are not looking for 100% accurate results because in engineering, there's always some bit of probability. Nothing is 100% certain. Okay. And we also have the other school of thought where you can superimpose and get this diagram right there. But again, I find this a bit tricky sometimes. So the best would be to either go with the first two or you go with the third one and then we ignore the final one. It's just that sometimes you go through some books and then you find some of these drawings in there so that it doesn't look strange to you when you come across them. Okay. So let's I think I just saw one more example on again on this. Do I have it? Looking for that example. B4, I think it should be on B2. Just to help us. I don't know if I don't think we did solve it. Okay, so let me reduce stuff over here. Just a second. Okay. So let's see. Let's have another example. Okay. So we have this beam. Um, Again, this is a simply no, I mean a continuous beam. So here we have uh, four supports in total. All right. And then let me try to figure out what is making this PC make all this noise. Okay. So let's say we have a UDL. Let me just draw the UDL, which has the same intensity throughout. So let's say 1.5 kilonewton per meter. So that's the intensity of the UDL. Um, and then we have so the length 5 meters, 5 meters, 5 meters. Okay. My five looks a bit funny. Okay, so this is A, B, C, and D. Okay, so the goal is to uh, draw the bending moment. And just draw bending moment diagram and then shear force diagram. Okay, so that's what we need to do. So let's go with our solution. So here you take three supports. So our goal is to look at span AB and then span BC. Okay. So if I take that span A, B, and BC, so I have this span right here, I can draw the bending moment diagram for these two spans. Okay, I'm to assume that the from here onwards, every span is assumed to be simply supported, right? So I can so if this is A and this is B and this is C, my bending moment diagram looks like this. It should be the same anyways. Yeah. And then the highest point here is what is WL squared over 8. Okay, so I don't need to go through first principle, find reactions, and find all of that if I can find my moment diagram. Okay, at this point we should look for these shortcuts. Okay. So here our W is 1.5. The L will be the spacing. So for this end, our L is 5 meters because they all have the same L and then the same load. It will end up being the same value throughout. So it becomes 1.5 times 5 squared over 8. And this will give us 4, let me just write the whole thing, 4,675 kilonewton meter. Okay, so at the top here, we have 4.6875, and here we have 4.6875. So now this is section 1. This is section 2. Oops. I thought that was going to work. Okay, so this is section 2. Looks a bit off, but at least. So section 2 and then section 1. All right. So for section 1, mm, for for area 1, that means that we have A1. where A1 will be 2/3 base times height, which will be 2/3 of the base is 5 and the height is 4.6875. All right. Then, so this should give us what would be the answer for this? Let's say 2/3 times 5 times 4.6875. So this will give us 125/8. Then now let's look for x1. So x1 will be the distance from the centroid towards the left end. So this becomes our x1. Okay. In this case, our x1 will be b over 2, or let me just say L over 2. Okay. So that will be, or let's say L1, so that we know which L we are looking at. So it becomes 5/2. Okay. So in this small space, I can have A1x1. So A1x1 would be, let's say 39.0625. Okay. And because area 1 and area 2 are pretty much the same, your A2, X2 would also end up with the same results anyway. If they are different, you calculate them differently, all right? But here in this case, they're the same, so I'll still end up with 39.0625. Okay. So if you come back to the problem, you would realize that A and D are the support at the exterior. Okay. Whilst B and C are the support or are the interior supports. Okay. So if you look at exterior support A and exterior support D, they are pin support or they are roller support. And because they are pin support or they are roller support, it simply means that MA is 0 and MD is also 0. At least we have established these boundary conditions. Okay. If the support were fixed support, they will not be 0. Okay. It's only when the exterior supports. So here, when exterior.
The
Yeah, hello.
did you say if the supports were fixed, they will not be zero, or
Exactly. Yeah, they will not be 0. Yeah.
but they are though, or I don't know. I'm confused.
If you have a fixed support, assuming you had a support like this on this end, let's say something
Oh,
like this, a fixed support here will not be 0. Okay.
okay, sir. Yeah, I
Here
understand.
M will be 0, but here M will not be 0. And again, here too M will not be 0. If you're looking at the the internal support, right? Okay. Let me just take this off so that it doesn't create confusion. Okay, so when exterior supports are pinned or ruler, the moment is 0 at least. Okay. So we could write our equation here. We know that for moment equation, I always like to just copy and paste. Just give me a second. Let me just copy from here and then paste over there. Where is this long equation? Okay, so let me see if it's going to work. I hope it works. Copy. Let's see if it's going to, oops, have this thing in the way. Sometimes you are better off rewriting everything than trying to copy and paste. My mouse is misbehaving. All right, so I think this looks okay. So let me take this all away. Okay. So we're using this equation because the I value, I is constant. Okay. So again, EI is constant, or I is constant. So because of the fact that EI is constant, we can cancel out the moment of inertia. Otherwise, then it means that our MA is 0. So I could just say 0. This is 0 plus 2 MB. We have L1 is 5, L2 is also 5, plus MC, MC times 5. We don't know what MC is. Okay. Even though you've taken these 3 spans, and then we have C right here, and then we have okay, always have in mind that C is not an exterior support. Yes, you've taken 2 spans, but from the main problem, C is an interior support. So C cannot be 0. It's important we take note of that. Okay. So that becomes minus 6. A1 is 39.06, okay, 0.0625 divided by 5 plus again 39.0625 divided by 5. Okay. So we have so all of this will be equal to 20 MB plus 5 MC minus 93.75. So we can clearly see that this equation has 2 unknowns. Okay. So we can't solve it. All right, because we would need another equation. And this is where you come and then look at the second span or the second set of spans. So in the first case, we looked at span AB, span BC. So it means that support B was our main support under consideration. So then we also need to look at support C under consideration. And to do that, we'll look at span BC and then span CD. Okay. Again, if the 2 spans will give us the same bending moment diagram, nothing will change because it's the same loading and then the same measurements. All right, so the same. So here, this becomes section 1. Always the section on your left is section 1, and the section on your right is section 2. It's important. If you compare the two, you would realize that initially BC was on the right, so BC became section 2. But once you move to the different set of spans, BC is now on the left. BC is no longer section 2, but rather, let's say, section 1 or area 1. Okay. It's important we always take note of these things. Okay. Because it has the same load, it has the same dimensions as everything else. It means that here our A1X1 would also be 39.025. And our A2X2 also be 39.0625. Okay. Nothing is going to change. Then our sets of equations will then be, so here, let me just make some quick changes. So here becomes MBL1, MC, and then MDL2. So these are the equations. Take note. The leftmost moment is now my MB, the centered moment is now my MC, and then the right moment is now my MD. Okay. So here, I don't know what MB is. I know that MD is equal to 0. but MC is not zero. Then MB is also not zero, all right, because MB and MC, these are interior supports. Okay. So here we have MB times 5 plus 2 MC, sorry, MB times 5 plus 2 MC 5 plus 5 plus 0 is equal to minus 6 into bracket 39.0625 over 5 plus 39.0625 over 5. So you end up with 5 MB plus 20 MC equals minus 93.75. And this will give us the second. So this will be equation 2. So we have equation 1 and equation 2. You solve the two of them. So solve. Let me make sure that this looks good over here. Okay, so solve both equations. Simultaneously. I think that's the word there. I think sometimes if I have the green lines, it helps to make the writing a bit better. I don't know why this is still in the way. Let me put you down here. Okay. Let's go with this. Nope. I think this is fine. Okay. Just so that it helps me with the writing. So if you have to solve both equations simultaneously, you'd see that from your calculator, your MB would be minus 3.75 kilonewton meter. And then your MC would also be minus 3.75 kilonewton meter. Okay. So now let's find the support reactions. Okay. So we can draw we have span AB, span BC, span CD. So this is A, B, C, and D. Okay. So we have these are moments. So these are the directions we assume they are in. We maintain these directions. Okay. And then just put the negative values on top. It's easier that way than trying to change the direction, because you could easily forget about changing the right directions, and then everything will end up being wrong. Okay. So now we need to find the supports. Find VA or RA, which are that is a step. Then we have VB1, VB2 for these supports reactions. Then you also have VC1, and then VC2, and then finally VD. Okay. And there's also a UDL on top. So let's not forget about the UDL. Okay. So if you treat each one separately, it becomes a basic structures problem. Okay. So you would see that our VA will be, this will be equal to, so this will be equal to 3 kilonewtons. VB would be, I think VB1 would be 4.5 kilonewtons. VB2 would be 3.75 kilonewtons. VC1 would be 3.75 kilonewtons. VC2 would be 4.5 kilonewtons. And then VDRD would be 3, 3 kilonewtons. So these will be your support reactions. Okay. So from here, you can draw your shear force diagram, okay, using one of the approaches. So let's say shear force diagram. Let me just draw it a bit nicer. Okay. So I have A. I think my B should be here, my C, and my D. I think so, yeah. So my shear force, this goes up here to 3, and between A and B comes down to 4.5. So I have this straight line, 4.5. Then it goes up to 3.75. Then it comes down to again 3.75. Then it goes up to 4.5. And it comes down again to 3. So here's 3, 4.5, 3.75, 3.75, 4.5, and then 3. So this becomes your shear force diagram. Okay. You can just shade it if you want, but I mean, there's no need to do that. So please, the lines are straight lines. My hand is not straight. It's not curved. Okay. Let me see if I can draw a straight line between these 2 points. Okay, so I think this one looks better. All right. So this becomes the shear force diagram. Okay. Again, we can draw the Benjamin moment diagram using either combining all or doing them individually. All right. Depending on whichever approach we go with, it should be easier to draw um, the Benjamin moment diagram. Okay. So in this case, if I have, different color would do. So let's go with black all the way to the end here. Okay. So again, we have A, B, C, and D. So between A and B, if I'm going with, so let me go with what we know. Up is positive, down is negative. Some can interchange it, it's fine. So we know that B, the moment at B is minus 3.75. So that we can put that over here. So our Venn moment diagram starts as a curve, then it comes down like that. Okay. Then it continues that way again. Then it comes down at the same point. So you have something like this. Okay. And it goes again to D. So this becomes a bend moment diagram. Okay. So here we have 3.75 coming from the moment at those points. We can easily find our max moments. All right. Because if we know this distance here, if we know that the distance here, x, we can easily tell what our max moment would be. All right. So this distance, I think, will be 2 meters. All right. So once it's 2 meters, you can easily find our moments, right? So it becomes 3 times 2 minus 1.5 times 2 squared divided by 2. So this will give us 3 kilonewton meter. It should be the same over here as well. Okay. And we can easily find the 1-2 at midspan for this one. All right. So that this becomes the Benjamin diagram. Am I correct? We can always check to make sure. I'm not too sure about this, but you can always check to make sure that we are doing the right thing. This one over here might not be as high as it's supposed to look like. It might just go depending on what the value might be. All right. Now let's look at some special cases. Okay. Let's look at some special cases. Actually, this is B4. What's my B3? Oh. So far, what we've been looking at is beams that do have supports at the ends which are simply supported. Okay. So what if we have a case whereby one end is fixed? So we could have something like this, or maybe something like this. Okay. So here's A, B, C, A, B, C. So what is changing now has to do with these fixed support at the ends. All right, so that's what is new. We are used to having pin support or roller support at the ends, but now we have fixed support. Okay. So here we are looking at case 1. Let me say case 1. Okay. Where some some or maybe all end supports are fixed or are fixed supports. Okay. So in the first, the one on the left, only one of the supports is fixed, but then the option on the right, the 2 supports at the extreme ends are all fixed. Okay. So in such a case, what do we do? If we are to use this example as it is, then we are forced to assume that, or we cannot solve the problem. Okay. Our option is to assume that support at A, in this case, let's say maybe this is the let's say maybe example 1 and example 2. So if you look at example 1, only A is fixed. Example 2, both A and C are fixed. Okay. So to overcome that problem, we create an imaginary span or beam, whichever way you want to look at it. An imaginary span or beam um, to the right or left, depending on the position of the fixed support. So here, one thing is that this imaginary beam or the imaginary span, or some would say virtual, okay? This has no length, there's no load, and then there's no moments. I mean, no bending moment diagram. Okay, or in brackets, no area. So I would explain what I mean by that. So if I take example 1, so here I'm looking at example 1. So with example 1, what happens is that for me to use the 3-moment equation method, I need to convert this right here, which is what we have. So this is pinned, and then the midpoint is ruler. Okay. Then translate this into a different option, whereby I still have my A, B, C. So I still have my A, B, and C. Okay. So again, I have my pin support, my ruler here. But with A, I create an imaginary span. So I create this imaginary span right here. Okay. On the left, because the fixed support is on the left, I create an imaginary support on the left. And maybe just name it OA. Okay. So that by naming that OA, if this is 2A, then I can assume this to be pinned or ruler. I mean, it doesn't really matter. So I can assume this to be pinned. Then this looks like the case where I can easily use my equation here. All right. But this span OA, here span OA is an imaginary span. Excuse me. All right. So this imaginary span has no length. So the length here is 0. There's no load on it. There's no area. Once there's no load, there's no length. You cannot find a bending moment diagram. So in that case, your area A is also 0. Okay. Now let's look at the example 2. Excuse me. So with example 2, I have this. This is A, B, C. This will translate into A, B, C. So there are fixed support on both ends. So I can have an imaginary span, OA, towards the left. And also have an imaginary span, maybe. I mean, you could name them separately. I mean, differently. You could name maybe, you can give it K or M or whatever. Just know that they are imaginary spans. Okay. So in this case, then my supports would be, so can we put a support here if I want, but it doesn't really do anything. to have support on these ends. Okay. All right. So again, span OA, why do I do 0? Span OA and the span CO prime are imaginary spans. So hence their L values, so that is maybe L1, maybe L4, whichever way you want to look at it, they are all 0. All right. And their areas will also be 0. Okay. So let's see, let's have a look at a proper example. Okay. Um, let's say I have this. So okay, we have W as our UDL, and then this is A and B. Okay. So here we can see that our MA will not be 0. Our MB would also not be 0. Okay. So to solve this particular problem, we convert it into the case whereby we can have pin support and then be able to solve them. So I come back here, have my UDL on it, all right. Then I change my supports to simply support or pin support. Then I create my imaginary spans, both on the right and left, because we have support on, fixed support on both sides. So this can become O prime, and then this would also be, there's always an imaginary. And this would be, sorry, this also be O. Okay. And then we have, let me just do it in a better way. O, A, B, O prime. Okay. So in solving it, we can look at span OA and span AB as our first set of spans. So it means that A is our span, or A is our support under consideration. Okay. So if I take just that section or just that part, I'll end up with something like this. Okay, so this is oops. So my Benjamin diagram will be like that. So this is OAB. Because between O and A, there's no load, so there's no moment. Yes, I'm trying to draw it to look like it has a length, but in reality, it doesn't have any length. Okay. So let me just draw this up to here. What I'm struggling to draw, then just do this as short dash lines. So at least we see the difference between the two. So the topmost part will be WL squared over 8. Okay, this we have been able to establish through many calculations. So here, A1 is 0, X1 is 0, L1 is 0. There's nothing when you look at the left side, which is the OA component, there's nothing there. But here, here becomes number 2. This is number 1, or area 1, area 2. Okay. So A2 will be half base times height. So it becomes, sorry, and 2/3 base times height. So it becomes, let's call this length L. Okay. Or L1. It doesn't really do anything. But let's call it L. It becomes WL squared over 8 times L. So this will give us what? WL cube over 12 our x2 will be equal to L over 2. So again, if we look at so A2 x2 will be equal to WL4 over 24, I think. Yeah, we can always cross-check these things. Okay. So I can write my moment equation, which I have it right here. Great. So here, let me change the notations a little bit so that we see what it does to us. Okay. Nothing really changes. It's just so that we appreciate. So this is M naught, MA, MB. Okay. The whole of the M naught here goes to 0 because there's nothing really there. All right. So it becomes 2 MA. L1 is 0. Okay. So we only have L. Okay. Then plus MB times L. Okay. So here L2 is the same as L. And this will be equal to minus 6. Again, this whole entire portion goes to 0. It becomes WL4 over 24 times L. Okay. So this will be, I can call this equation, so let me just call this equation 1. Oops, not what I was looking for. So let me call this equation 1. Yeah. Okay, this is equation 1. Then I can look at the next span AB, and then BO prime or some other naming. Okay. So with that span, so this is this is AB and then O prime. Again, it's best I okay, this is even better. All right. So this is an imaginary. So again, I have my bending moment diagram right here. Let me just draw. Sometimes it's best to do the stroke erase rather. So this is my bending moment diagram. It looks a bit funny, but then the topmost part is WL squared over 8 right here. So my A1 will be the same as the other A1. So my A1 here will be WL cube over 12. My X1 will be L over 2. So A1 X1 will be WL4 over 24. A2 will be 0. L2 will be 0. Okay, because again, this is imaginary. So imaginary. So if we were to use the same equation, you would see that, let me just rewrite the whole thing here again. At some point, I'll be simplifying things so that I don't need to be rewriting the equations every time. Okay. But so that we follow what is happening, that's how come we're going through first principle. So here, let me change my lettering. Okay. So I have here MA, MB, and then MO prime. Okay, yeah. Just for the fun of it. So MO prime goes to 0. The A2X also goes to 0. So we have MA times L plus 2mb times L will be equal to minus 6 WL4 over 24L. You can again simplify this. Okay, so here we have our equation 2. So we solve equation 1 and 2 simultaneously. Okay. And once we do it that way, we'll see that our MA is equal to minus WL squared over 20 over 12. Is it 12? Yeah. And then MB will be equal to minus WL squared over 12. Am I correct? I think so. If not, then again, you can always check these things. I mean, excuse me. um, no, yeah. So I'm correct. All right. Okay. So based off of this, from here, we can draw bending moment diagram and shear force diagram. Okay. That I'll leave it for you guys to practice with. Okay. So these are one of those special cases. There's also a second special case to look at. So this is everything we've done here is for case 1. Now let's look at the case 2. Where we have, so case 2 is where we have overhangs or overhanging beams. Okay. So let's see I have this beam here. Um, yeah. So we have a load. Let me change the color of the load. Okay. There is some load somewhere. Then we have a load here, P. This length here, L3, L2, L1. Okay. So we can see that this portion, oops, let me name it A, B, C, T. So let me call it span. So span CD is the overhang. Okay. Which means that technically when we are solving this particular problem using the 3-moment equation method, we don't need to create a separate span for CD per se. So we can rewrite this equation for the purposes of just the 3-moment equation, right? And then come up with another option, which would be to reduce the overhang. Why can't I draw a straight line? Okay. So again, I have this support here and that. Okay. So again, I have my A, B, and C. And then the load P at D will cause a moment at C. Okay. And that moment at C will simply be P times L3. So I can actually have a moment, and this is a clockwise rotation moment about C. So I can have a moment at C, which will give me PL3. So I can convert this equation here into this right here for us to solve. Okay. So I can use this approach in solving beams that do have overhangs. Okay. Now let's look at an example. So maybe that'll help us to appreciate. So let's call this example 2. Okay. So this example, I'll do it in such a way that I have both a fixed support and then an overhang so that we can do more than one item. Okay. So let's say it has a UDL, which is 10 kilonewtons per meter. The length here is 12 meters. Then this is 6 meters. Then we have a load of 100 kilonewtons. Okay. So let's say EI is constant. We don't need to go through a lot of calculus. So EI is constant. So this is A, B, and C. All right. So I can take this information here and converting it into a much more suitable option for us. Okay. So the suitable option would be I have AB. I have AB here. Then I have my imaginary span. So let me call it O. And then because of the fact that BC is an overhang, I can have that overhang right here, which would be 100 times 6, which would be 600 kilonewton meter. Okay. Then I have my UDL as it's supposed to be over here. Okay. So let's try looking at it. No, let me just take the UDL off. I'd rather draw the Venn moment diagram. The Venn moment diagram for this section. Oh, look, this is funny. Let me just draw it a bit more. Okay. It will look like this. All right. Where the topmost portion here will be 180. 180 kilonewton meter for the topmost portion. And how did I get that? I used WL squared over 8. Okay, so that is 110 times 12 squared over 8. Okay, and that'll give me 180 kilonewton meter. Okay, so once we have that, we know that, let's find A1. A1 will be for section 1. So our A1 is 0. It means that, or let's say A1x1 is 0. So I don't need to write it. A1x1 is 0. Let's find A2. A2 is 2/3 of a base of 12 times a height of 180. Let me just jump. A2x2. Okay, so that we just move times 12 over 2 for the AX2. Now give me 8640. Okay. So once we have that, we can formulate our equation. So in the end, you end up with 2MB times L plus, let's say MB, 2MA times L, and plus MB times L equal to minus 6 into bracket A2X2 over L2. Okay, so this becomes the simplified equation for this particular problem. Okay. So let's see, this is This is also the same as L anyways. All right. So I can end up with 2MA plus MB equals minus 6 A2X2. Okay. Am I correct? No, I'm not correct. Okay. So you know what? Let me just leave it as it is so that I don't confuse you guys. This is fine. Let me just go with this method. Okay. So here our MA, we don't know what M is, so it becomes 2MA. Our L is 12 plus MB. Our L is again 12. Then we got to minus 6 into bracket 8640 over 12. Great. But because of the overhang, okay, which gave us the 600 kilonewtons at B, it means that we already know what the moment at B is. So the moment at B would be 600 kilonewtons. Okay. Now we need to take into consideration the direction of the moment. The moment at B is causing an a hugging moment or a negative moment. So it means that in actual fact, this is minus 600 kilonewton meter. If we are to look at the fact that these directions are the positive directions or are the sagging directions. Okay. So our equation then becomes 24 MA plus into bracket minus 600 minus 600 times 12. This will give us whatever. Let me see if I can do the computation quickly. It's 640 divided by 2, I guess. Yeah. So we get 43, oops. So minus 4320. Okay. So we can go ahead and still solve it. So we get 24 MA. This will give us 7200. So minus 7200 equals minus 4320. So our 24 MA will be equal to this goes towards the other side. So we get 2, am I correct? 2800. So our MA, I'm hoping I did not this will give us 120, sorry, 120 kilonewton meter. Okay. So this is our MA. We already know what the other moments are, so we are good, right? So we know MA, we know MB, so we are good to go, all right? So from here, we go back to our problem and then solve for the support reactions. Okay. So let's go. Find support reactions. And then draw bending moment diagram and then shear force diagram. Okay. So let's see. I mean, let's just go through it just time around, just solve for all these support reactions. So now that we know MA, so I can come back here. MA is 120. Okay. So I maintain the positive directions and I maintain the value as well. Okay. So we need to find VA, find VB, And then we have this load of 100 kilonewtons. Then we also have the UDL. Oops, let me just change these ones so that so this is 10 kilonewtons per meter. This is 100 kilonewtons as a load acting downwards. Then we have a moment which we calculated for. Then this again becomes the case of a simple beam in basic structures. So this is 12 meters and this is 6 meters. Okay. So let's say if we sum moment about A, which is easier. So summation of moment at A equals 0, then it means that we'll end up with 120 plus those 100 times 12 plus 6 is 18. Then plus 10, this 10 times 12 over 2. If you don't get anything, you can let me know. All right. What am I looking for? Okay, right here. Then minus VB times 12 equals 0. Okay, so let me see if I'm correct. So we can do the math over here and see what the value of VA would be. what the value of VB would be. And I think VB will end up being 120 kilonewtons. Again, just cross check it. I'm pretty sure I'm right, but we can always cross check it to see. Yeah, that should be correct. I hope I'm correct. Let me just make sure everything looks all right. 100 times 100 times 18 is correct. 10 times 12 times 12 over 2 and
Yes,
be,
I
yeah,
think the answer is 220.
220 rather.
Yes.
Have I made a mistake somewhere? It's supposed to be 120. I'm coming. Okay, let me see. 10 times 12. Okay, yeah. It's 220. All right, it makes sense now. All right, thank you for the corrections. Okay, great. All right, so 220 kilonewtons. Now let's find VA. VA plus VB will be equal to 100 plus 10 times 12, right? So this will give us 220, which means that VA is 0, right? So the reaction at A is 0. Once VA is 0, our shear force diagram will look like this. So it's 0 over here. Then it starts going downwards, negative to 120, then it jumps to 100, then it goes this way. Okay, so this is 100 and this is 120, so negative, positive. So this is the shear force diagram. Okay. Then for the bending moment diagram, again we have it this way. We already know that the support moment is 120, so there's a huge jump of moment of 120. Then I can find a key point. You need to find your moment A and B. All right. So the moment at B is minus 600. We already had that at the very beginning of minus 600. So that will be a negative moment right here. Okay. So this will be a straight line because the moment is straight. Then between A and B, we have a UDL. So that will be a parabola or parabolic diagram. So we can end up with something like this. This doesn't look parabolic enough, I guess. Okay. I'll try and make it as parabolic as I can make it look like. Okay, so this is parabolic. All right, good. So here we have 120. Then here we have 600. Okay, so this is a positive and this is a negative. So here's a straight line. Let me just delete that and then draw it with a straight line just so that we know it's a straight line. Okay. All right. So this becomes the bending moment equation and the shear force, bending moment diagram and shear force diagram for the case where we have these two support conditions. So here, with this example, I incorporated the fact that one end is fixed and one end also has an overhang. Okay, there are many examples out there, but once we get the concept right, we should be able to solve problems involving any of these cases. Okay. So I think we've gone through pretty much all that we need to do for this particular topic. This should bring us to the end of three-moment equation method. Okay. Yeah.